Good morning, fancy meat computers. How's everybody doing today? Oof. Just not play with that then. How is everybody today? Currently 13 people, 14 people watching. We'll just give people a few minutes to show up. Amazing. Great. Wonderful. Oh, are they posted to Avenue? No, they're not. Let me take care of that quickly. There. That should be... You should now be able to see topic 9 hash tables. No more midterms. Feeling a little happier, but only a little bit. Ha! Have you heard anything about the SAS students' midterms? Oh my god! Frigging these people. Like, go talk to them. I have authorized people to write at different times. I've talked to these people about 5 or 6 times about this. It's like every single student who has to write the test with SAS has to be, like, they have to be told separately for each one. It's like, and every single, like, every single time they're claiming, like, I've had, like, every single SAS student come to me separately and say that there's, like, nothing set for it and they don't know what they're doing. And it's like, I have told them, I set them up with all of this on Monday. They have had the information since Monday. Go tell them to check their email. I'm getting so sick and tired of these people. Like, Jesus Christ. Ugh. If you're a SAS student and you haven't already written your midterm, please get them to write it. Get them to give you a slot as soon as possible. Please. Because we're starting to mark them. And we need to get these things out. Please. Like, they have the information. Okay? They have it. I've told it to them multiple times. They're just being dense. That's all. Bloody bureaucrats. Like, they've put a new thing in right? There's a new policy that they're putting on the letters now that, like, tests should be written in the SAS testing center whenever or wherever possible, or, you know, a certain number of people have it on their letters that they must write in the SAS testing center, and it's like, okay, sure, but if the center is actually incapable, right, of actually performing the operations that they claim they're able to perform, like, it would have been simpler at this point for me to just do the accommodations in class. Way, 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 way simpler. Okay, anyway. Enough about that. So let's talk about some course material then, shall we? I'm sorry I'm sorry for I'm sorry for dumping that on you guys. It's very frustrating, and it gets frustrating after a time, you know? Like, anyway. So, last time we finished off our discussion of tree balancing, and now we are on to something completely different. It's completely different in that we are no longer talking about trees. We are no longer talking about any of our traditional approaches to the searching algorithms, but we are in fact still talking about search algorithms. Hash tables are a type of search algorithm. They are a mechanism for organizing data such that that data can be retrieved quickly and easily. So, hash tables are normally applicable when the type of data that you're searching for is of a particular, it needs to have certain qualities, right? So, in general, before anybody asks, I am not sure. I don't know what the exact mechanism of the hash tag is. I imagine it's related to a hash table, but I'd have to look into the matter, and perhaps I will before the end of all of this. But you should be thinking like a hash table. The correct thing to do at this point is to sort of forget the fact that you've ever heard the term hashtag or hash anything. Start from a blank slate. We're going to build this up. All right? Cool? Let's get started then. So, here's a summary of our symbol table implementations so far. Sequential search performs terribly. Binary search performs better but still not great. Binary search trees have good average case performance but bad worst case performance. Red-black trees have good average case and worst case performance. Can we do better? Yes. But we have to be able to access the data differently. So, with respect to hash tables, right, we are going to attempt to produce some algorithms that can outperform logarithmic time. Right? So you might be saying, but Mr. Professor, sir, we've been saying all this time that logarithmic time is about as good as you can get. How can you get better than logarithmic time? Answer: constant time. The unmitigated holy grail of all runtimes, constant time access. That's what we're shooting for with hash tables. So, a hash table is a data structure used to implement dynamic sets and symbol tables. So, hash tables are used to implement the same stuff we've been using binary search trees to implement. Our operations of concern are find, search, find or search, right? Find and search are the same operation. Insert and delete. We want constant time, at least on average, for each operation. So at this point, we're okay sort of, you know, we're okay letting go of a logarithmic time worst case scenario if by that we can gain a constant time average case scenario, right? So, hash tables are typically used when the number of keys stored is far less than the number of all possible keys. So, for example, if the set of keys we're talking about are something like the natural numbers, when you have a small number of the natural numbers actually used, in comparison to, you know, the number of available numbers in a 32-bit unsigned integer, just to pick a random example, then you're in a situation where a hash table is probably going to be useful. So how can we manage to get constant time lookup? Right? Well, direct addressing in an array gives you that, right? So if you take an ordinary array, right, we can look up a particular element in an ordinary array in constant time, right? And if, you know, I have some disagreements. I apologize. I have not had time to edit these slides as I've been editing the slides so far in the course, so I will have the occasional disagreement with the slides. One disagreement that I'm having with the slides immediately is it's claiming here that direct addressing into an ordinary array enables search, insert, and delete in constant time, right? Like, that should be a little more specific. We're not talking about taking a static array, being able to put an element into the middle, and expanding the array that way. That is still a linear time operation, and that's not what they're talking about here, right? Same thing with deletion. Taking an element out of the middle and collapsing the rest of the data structure around that now missing value. That is still a linear time operation on arrays, right? That has not changed. This is a different type of mechanism we're talking about, right? The direct addressing scheme is that you take an array, right? You instantiate it to be as large as all of the elements that could ever possibly be put into it, right? So you've got one slot for every possible key, right? In that sense, inserting an element into it is constant time, because inserting the element does not mean expanding the data structure. It just means using a previously unused but declared value inside of the data structure. The same way, deletion is not collapsing the data structure. Deletion is simply setting to null the element stored at some particular index inside of the data structure. Is this making sense? Can I get a thumbs up if you guys are understanding this distinction? Right? Furthermore, on the subject of searching an ordinary array, right? Searching in an array is still a linear time operation, right? But if you're taking search to mean searching in the symbol table sense, which is to say, I have a key and I'm trying to return a value, right? If you've got an array with one index for every key, that those keys can be looked up in constant time and the values returned in constant time because you know where in the array each key is stored. It's stored at an index equal to the key, right? Kieran says, would this not take a lot of memory? Kieran, you have hit upon the entire problem with this whole scheme. Yes, this would take a lot of memory. But what we're trying to do is we're trying to take those characteristics of direct addressing in an array, and we're going to try to convert it to a data structure that's much more memory efficient than this, right? Yeah, this would take quite a lot of memory, right? This would take a number of, like, the size of the array would have to be the size of all of the possible keys that you could possibly get. So if your keys are something like 32-bit integers, right, the amount of memory that it would take to represent all of that, let me just pull up the googs and do a small calculation. 2 to the power of 32. What is the Google celebrating jollof rice? Oh, that just seems like a sponsorship, man. That just seems like a sponsorship. Friggin' Google, man. So this is the amount of this is the number of, like, this is the number of integers you would have to store in memory, right? So since an integer is 4 bytes, this is the number of bytes you would have to store in memory to be able to do that. So you can see that that's a megabyte, that's a gigabyte, those are the gigabytes. So you would need 17 terabytes of memory to be able to keep a complete symbol table for, you know, if you wanted to take a 32-bit int and make that your key, right? This is a lot. That's impractical. The fact that, you know, we have terabyte drives now, you know, does not make that practical because it needs to be stored in continuous memory, right? You would need, you know, 18 terabytes of RAM to be able to accomplish this, right? So, how do we fix this situation? We use what is known as the hash table. Hash tables typically use an array of size proportional to the number of keys actually stored. So, basically, you have what's called a universe of possible keys, right? And then you have the size of the set of keys that are used in a more practical sense, right? So, throughout the coming slides, magnitude U means the universe of all possible keys. That is to say, the set of all possible keys. And then K is the set of keys that we're actually concerned about storing, right? Because, and basically, hash tables, one of the conditions that make hash tables practical is if the set of keys that you're actually interested in storing is much less than the set of all keys that it's possible to store, right? This is what the two, in math speak, that's what the two greater than signs mean, or the two less than signs mean, is much less than or much greater than. So we have to kind of think in terms of, so we've got the universe of all possible keys, but we need to think about how many entries we actually want to have in the table, right? We have to have some sense of how big the table needs to be. So, hash tables, instead of using the key as an array index directly, the array index is computed from the key using the hash function. Hash functions are without the hash function, You would just be back stuck in the direct addressing situation, right? What we do is we compute a hash value from the key. That hash value becomes the index, and then we use that index for direct addressing. All right? We're gonna see examples. So, let's imagine that the universe of keys, U, which let's say is from 0 to n, is very large, and the actual set of keys that we want to store is small in comparison. So m and n is much larger than m in this case, right? We could simply use an array or direct address table for t from 0 to m minus 1. Every slot will correspond to a unique key in the universe U, and if the key k is absent, in the actual key set k, then we set t at k to nil, right? So to state this another way, right? So you set an array, right? You create an array. This is the array itself is called the hash table. You create elements in the array going from 0 to m minus 1, right? So where m is the size of k, which is the set of keys that we're actually concerned about storing, right? So you have this array going from 0 to m minus 1, right? Every key will hash to a slot in that array, right? And if there's nothing currently that hashes to that slot, you leave the slot open, right? You set it to nil and you leave it open, right? It turns out that what we want to actually store in the table is not the value itself in the key value pair, right? We want to actually store that in what's called satellite data. We want to separately instantiate that. The array itself will contain a pointer to that satellite data, right? That's going to become useful later on. But yeah, so adding something to the hash table, like if we get a new key and we want to add it to the table, right? We compute the hash of that key. We look up the array element corresponding to that hash value, and then we instantiate a new satellite node and link to it, and that fills that slot. Does that make sense? Are we good so far? Can I get a thumbs up? And if you have any questions, please take this opportunity to ask your questions. Good. Getting some thumbs up anyway. So is the hash table not a static array? The hash table itself is a static array. Yes. In theory, you could expand it using dynamic memory allocation, but you'd also have to change the hash function so that it will, compute inside of the range, the new expanded range of the hash table. Why is this more efficient? Excellent question, but we're getting there. We're getting there. But basically, this means that a lot of things can be computed in constant time whereas previously we required logarithmic time to access it. So let's talk before we move on then, just because it's come up, let's talk about how you would get information out of one of these things, right? So let's imagine this as a symbol table. Let's perform a find operation over this hash table. Let's say we are looking for, some key, right? The first step for searching is we compute the hash of the key that we're looking for. Now, computing a hash takes the same amount of time no matter how many elements there are in the hash table, obviously. All you're doing is, performing some arithmetic, right? You might be performing quite some arithmetic. It depends on how complicated the hash function is. But no matter how big the table itself is, the arithmetic can be performed in constant time. So deriving the hash value itself is a constant time algorithm. Index lookup in a static array is also constant time, right? So once I've computed the hash value, let's say the hash value is 5, right? To find the fifth, or the element with index 5 in an array, that's a constant time lookup. So retrieving this pointer, also constant time, right? Then we follow this pointer and retrieve the value stored in this node. Following a pointer and accessing a node, accessing a struct field, or accessing the field of a class, something like that, those are also constant time. Operations. So we have 4 constant time operations which allow us to perform a search on a hash table. Whereas, even with a red-black tree, we had to trace through a number of nodes proportional to the total number of nodes stored, right? So, hash tables constitute an improvement over binary search trees and balanced binary search trees because they permit constant time searching without spending too much memory, right? So hash tables are basically our classic example of spend some memory, get some runtime, right? But in this case, we're doing some clever memory stuff to not have to spend more memory than we need, right? But that also requires us to know, roughly how many memory slots we need initially. What's the difference between a symbol table and a hash table? Everything that we've talked about for the last 3 topics, this topic and the last 2 topics, those are all ways of describing symbol tables, right? A symbol table is just a way, it's just a way of retrieving values given a key. Anything that retrieves a value given a key, kind of like a Python dictionary, these are all symbol tables, right? So, binary search on an ordered array, where the array is composed of key value pairs and you're searching the keys, that is a symbol table, right? There's a very large number of actual underlying data structures that can implement a symbol table, right? It's kind of like how with union find we had a very large number, we had 4 different ways of storing in memory and performing the same interface. Let me put it this way. Symbol tables have an API, right? Over the last number of topics, we've just been discussing different and increasingly efficient ways of meeting that same API's expectations for behavior. In the same way that with union find, we started off with an API, and we did 4 different variations on data structures, underlying data structures that will satisfy that same API. So, good. The static array contains pointers pointing to satellite data, correct? Yes, and we're going to see why very shortly. Right? So let's continue on, shall we? With direct addressing, an element with key K is stored in slot K. Wait, question. So does this mean we trade memory for runtime in hash table? Yes. Yeah. The price that you're paying for the hash table is all of these unused slots, right? The slots, you may have some unused slots in a hash table, right, for keys that aren't being used, because ideally you want to make the hash table as big as, you know, all of the number of keys that you could possibly ever want, right? But no bigger than that. You don't want like one for each integer, but you want to have one for each key that you might run into, right? So you're going to be spending memory there. That's, yeah, so this is a classic spend memory, get runtime kind of situation. So, with direct addressing, an element with key K is stored in slot K. With hashing, this element, an element with key K is stored in slot H of K, where H is the hash function. H maps the universe U of keys into the slots of the hash table. That is to say, H is a function from U into 0 to m minus 1, where m is much less than U. We say that an element with key H hashes to slot HK. We also say that H of K is the hash value of key K. The hash function reduces the size of the array size from the magnitude, or sorry, the cardinality of the set U, right? The cardinality of the universe of possible elements to m, which is actually the actual number of keys stored. Make sense? So far, so good? So, here's a problem, though. Since m is much less than u, two keys may hash to the same slot. That is to say, for k1 and k2, and some k2 not equaling k1, both elements of u, h of k1 might be equal to h of k2. This is known as collision, right? So, because we have this mysterious hash function, which, you know, we may not even necessarily know how it's computing hash values, it's entirely possible that we might be able to put two elements of u into it and both times get the same hash value out of it, in which case we are trying to write two values to the same slot in the hash table, right? This causes what's called a collision. Obviously, with our conception of hash tables that we have so far, one would overwrite the other, or something like this, which is undesirable behavior, right? Because if we think back to what a symbol table should require, right? For two keys to have their values interfering with each other is contrary to, like, what we would expect, how we would expect a symbol table to behave, right? So how do we fix collision? Does anybody have... I'm going to leave this open to the class. I'd like a suggestion from the class. How do we fix this? How do we fix collision? We could move it to a different slot. So if we move the hash value to a different slot, what happens when another key hashes to that slot? right? We haven't actually eliminated the problem of collisions. And, you know, moving it to a different slot means you have to search the array for a spot that's empty, right? And searching the array for a spot that's empty, first of all, it might not have an empty slot. And second of all, that's going to be proportional to the size of the array. So you've introduced a big O, you've introduced a linear operation, which you don't want to do. Check to see if there's already a value there. I mean, yes, but, you know, what if there is a value there? We still need to store the data somewhere. Our hash function needs to be one-to-one. Ideally, it is, but we can't guarantee it. That's the whole problem, right? Could we modify the hash function whenever we add a new element? That also doesn't resolve the issue of collision, right? Because, you know, if you have hash function version 1, hash function version 2, and you put two different numbers into them, they can still come up with the same number, right? It's still possible for them to come up with the same number. Add a new slot to the end of the array, which is constant time. Yeah, but then you have to modify the hash function each time, and if you modify the hash function, you might lose the existing relationship between keys and their hash values, right? So you'll scramble the table if you try to add to it. Make a key that points to another key. We are getting closer to the answer there. Make a list of key value pairs under the same hash value. Yes! Why would a hash function with a unique key input produce the same output? Because you're going from, like, many to few, right? The universe has many elements. The set of hash values is small in comparison, right? So you can't guarantee, like, as we'll see when we talk about what constitutes a good hash function. We're going to see that, like, you know, one way that you can do this, right? I'm just going to pull up Python for the Python interpreter for just a minute. Python 3. So let's say we had a universe that was, like, 1,000 elements range. A universe that consisted of 1,000 elements, right? There we go. Let's say that we had a key. Let's say that we only were interested in storing 50 of them, right? So the set of K is list range 50, something like that. So how do we go from this guy to this guy? Well, one way you could do it is K. So you could say def hash K, or I could say h of K. That would be even better. Return K mod 50. You'll find that a lot of these functions end up relying on modulus operators, right? So, if this is true, then, you know, assuming you're sparsely picking a few numbers out of this universe, right, we would still have things like h at, 64 hashing to the same value as h at 164 or h at 564, right? In order to create a hash function which narrows the scope this way, every element of the universe must hash to some value, right? We're relying, sort of stochastically relying on the sparseness of the usage of the universe to say that this is going to be a seldom occurrence, right? But, there are 20 different values inside of the universe which all hash to 14, right? And that's an inextricable problem. right? So, your colleague who said make a list of key value pairs under the same hash value was correct. So what we do is we chain them. Rather than just have our hash table point to a single node with key and satellite data, instead it will point to the head of a linked list. Ta-da! Good. I'm glad that makes sense, because that's like an important mathematical point, and I'm sure that the rest of the class benefited from having seen that. So thank you very much for your question. That was an excellent question. So in chaining, we place all the elements that hash to the same slot into the same linked list. So basically, rather than linking to single values, the pointers in the hash table are now pointers to linked lists, right? So this is getting kind of complicated. We're throwing in like we've got arrays in here, we've got hash functions in here, now we've got linked lists going on, But this is like, if you're trying to do something practical with programming, you are definitely going to have to produce these types of composite data structures. So there you go. Don't we lose constant time lookup now? That's an excellent point, Kieran. Yes, there is a price to be paid for dealing with collision. But let's leave that until the next slide where it's discussed. So, in chaining, we place all of the elements that hash to the same slot in the same linked list, right? So, if we have, for example, keys 2, 7, and 5 all hashing to this element in the table, we place 5, 2, and 7. We place them inside of a linked list linked to by the hash table. Slot J contains a pointer to the head of the list of all stored elements that hash to J. If there are no such elements, the slot J contains nil, or null, whichever you want. So there you go. We now have a many-to-one relationship between the set of actual keys used and the hash table. So, what price have we paid? In terms of insertion, if we are not concerned about the orderedness of these linked lists, then we can insert in constant time, right? If we are you can just follow it through, plunk it at the top, and boom, constant time insertion. If we need to search through the DLL, do we just introduce big O N? Yes. So let's talk about find then. To search for an element k in the list T at H at k, the time complexity in the worst case is M. So the absolute worst case scenario is that every single one of the values that you're trying to hash have hashed to the same value. It's kind of like with binary search trees. The worst case scenario is very improbable, but it's like kind of out of your control because, you're not necessarily in control of the order in which things get added to the structure. With hash tables, if you have written a hash function that hashes every single element in the hash table to the same value, you should reconsider your hash function, right? However, that does mean that the theoretical upper limit to the size of this linked list is the number of elements in the hash table. So that means that both find and delete now have linear worst case scenarios. On average, it's going to be much, much, much less than that. We're kind of in a quick sort situation here where worst case scenario, we're not performing any better than just linear search or like the linear way of going about things. But on average, we are doing far, far better than that. far better than that. Make sense? Hopefully. Yeah. So I'll pause here for questions. Also, I have a question for you, for all of you smart kids in the class. So, under the scheme that we have right here, right? This creates a linearized, like the problem becomes linear, right? Can you think of a way of getting the worst case scenario down to a logarithmic, to be logarithmically proportional? Shouldn't time complexity be big O, the size of the universe divided by m? No, the number of slots in your array is m, right? Oh, no, I see what you're... No, I see where you're coming from there. We are not concerned... We're not concerned with storing every value in the universe, right? The whole reason that... Like, the reason that hash tables work is because we have, like, this cap on the number of used keys, right? It's not the entire universe. And yes, make it a BST, make it a tree instead of a linked list, point to a tree instead of a DLL, yes, or a DDL, LDDD, LLL, doubly linked list, yes. Yes, thank you, Boffins. You are correct. If we were to substitute these doubly linked lists for a more complicated or efficient data structure, like, say, for example, a red-black tree, then we would be able to get much better performance out of this hash table than just simply having to revert back to linear time. So, if we do that, we're talking about find and delete operations that are actually still proportionally no worse than the red-black tree or the balanced trees that we were talking about previously, but we managed to acquire, well, insertion would also, like, you'd pay a price on insertion as well, right? Insertion would no longer be a constant time algorithm because, insertion into a BST is logarithmic as well, right? What the hash table then becomes is it becomes a scheme for dividing up the tree to a large number of small trees, right? Would you rather have one BST with 1,000 elements, or 100 BSTs with 10 elements, and some way to get to them in constant time, right? It's more efficient. Hash tables are more efficient. So, the probability that h of k is equal to h, question. Can we just have nested hash tables to always get constant lookup time? Could we nest hash tables? So if you've got multiple keys that hash to the same value, and then you're storing a hash table inside there, which is like the expected number. Okay, no. Okay. Here's the reason that's inefficient, right? So if you have a hash table, right, you have one slot, the size of the hash table is m. The size of each subtable would also have to be m, right? So what you do is you explode the amount of memory that you need to store from m to m squared, and M might be reasonably large, so you should probably not do that, right? Like, in theory, you could do it. But that also doesn't solve the collision problem, right? You could have two keys which collide against two different layers of the hash table, right? So I admire your ambition, but I don't think that would actually. I think you definitely hit the point of diminishing returns there. Like, the runtime memory trade-off is good, but at a certain point you do have to worry about using too much memory as well. Okay, well, there we go. All right, that's the end of class. If you have any questions for me, please submit them now. Ugh. Otherwise, we'll try not to bake a complete hash of it. Jokes! Jokes! Take her easy, folks.